All right, so let's try this. Okay, so if we have a circle with a given center, let's say A, and pick a point on the circle, B, and notice my language here. On the circle means it's going to be on that circumference of the circle. Point A, the center, is not on the circle. We'd say that's inside the circle. And so this distance from A to B would be the same distance if I picked any other point on the circle, say C. The distance from A to C would also be the same because they're all equidistant, and we refer to those as a radius or radii. So we say that AB and AC are radii, which is plural for a radius, of circle A. And so when we name a circle, we name it by its center. Also, by naming the circle, you know, okay, that point A is for sure in the center of the circle because my drawing may not look like it, but that right there will confirm, yeah, that should be the center of the circle. Okay. So when we're looking at these angles that form, so this angle right here formed is what we call a central angle. A central angle is an angle with with a vertex at the center of the circle. Okay. So in the example above, we would say that angle BAC is a central angle of the circle. Let's say that angle measurement is 80 degrees. Okay. When you have a central angle, the central angle is going to intercept the circle at a couple points. And so in this case, our central angle is intercepting the circle at point B and point C on the circle, and that it kind of divides our circle into two parts. You have the part right here from B to C, which we call our minor arc. And then we have the part from B to C going the other direction, which is what we refer to as the major arc. And we'll usually put a third point on here to distinguish between the directions. So we'd write something. Well, let me define those for you. So an arc measure is equal to the measure of the central angle intercepting that arc. So, for example, in this one above, we could say the measure of arc BC, written this way, so I write BC with this little arc symbol above it, would be the same as the measure of angle AB, or BAC. Okay, so because that's the measure of the central angle intercepting it, and we see in the picture that they're both equal to 80 degrees. And so often we'll write 80 degrees on the outside of the circle to say, okay, the measure of my arc BC is 80 degrees. If I want to talk about the measure of the larger arc, the major arc from B to C, we usually use 3 points. So starting at B, going through D, and ending at C. So that signifies our major arc. What would that measure be? 280, right? Because it's the rest of the circle. A full circle is 360 degrees. So if we say, well, 360 minus the 80 would give us the 280 degrees, right? So we'll add to this a minor arc has a measure less than 180. Whereas a major arc has a measure greater than 180. All right, so I've been giving you some notation and some definitions. I still have some more to give you, but we're going to take a break from that, and I'm going to give you an example of a problem that you might encounter using this information. So example 1. I'm going to give you a circle. Every problem in this unit is going to have a circle. And the central angle intercepting the circle at points A and B here. Let's put a point C here. And let's say that center of the circle is going to be point D. So I'm going to give the name of the circle. It's called circle D because we name it by the center. And I'm going to tell you that the measure of angle ADB is 100 degrees. And the measure of major arc ACB is x squared plus 251 degrees. So find x, or solve for x. I'm going to give you a second to try that out. Draw on the picture as much as you can and solve for x. So on this one, we're given that ADB is 100 degrees. And so, I'd sketch that in there. And by what I told you, well, that's the central angle. So that's also the measure of this arc. So I'd also put 100 degrees out here. So AB is 100 degrees. And then that's the minor arc. So if the minor arc is 100 degrees, what would the major arc be? 260, right? Because they're gonna both add up to 360 degrees. Okay. Wonder what we call that. So like two angles that add up to 90 is complementary, right? Two angles that add up to 180 is supplementary. What's two angles that add up to 360? Circular, I don't know. Okay. So we have that, but we're also told that the measure of that major arc is x squared plus 251. So we can set that equal to 260, and that gives us an equation to use to solve for x. Now we've worked with quadratics already, and we have a method that we use to solve for variables using quadratics. What's that method? Set equal to 0. So subtract 260 from both sides, and you get x squared minus 9 is 0. And then, what do we do? No, we factor. And there's like 5 types of factoring that we learned. You gotta pick the right one. This one would be a difference of 2 squares. So x plus 3 times x minus 3 equal to 0. Set each piece equal to 0, each factor. And you end up with x is negative 3 and x is positive 3. So it's been a little bit since we factored. I'm bringing it back. Every homework will have at least 5 factoring problems to give you practice, and the test will have factoring on it as well. So you want to bring it back and get used to that. Okay. All right. Let me go back to defining some things for you. So a segment with endpoints, with both endpoints on the circle is called a chord. C-H-O-R-D. Okay, so that's what we mean by a chord. It's a segment that has both endpoints on the circle. When we say on the circle, it means on the circumference of the circle. So a radius is not a chord. The radius has one endpoint in the circle and one on the circle. You need both endpoints on the circle. So for example, pick any 2 points. So let's say this is A here, this is B. Okay, connect them. That's a chord, right? Or if I put another one here, we'll put C here and D here. That's a chord. Okay. Now, if you have 2 chords that are congruent, let's say AB is congruent to CD in this picture, then we can find out some extra information. And here's how. So here I'm going to kind of do a little verbal proof. Again, I'm de-emphasizing proving in this unit just because we don't have time to do it. But there's a lot of proofs that we could get into. I'm just not going to focus there. But we're going to do a little quick proof here. So if I draw these 2 triangles, okay, what can you say about these 2 triangles? Let's put E here. What are they? I don't know that they're vertical angles because I don't know if like CEB is really a straight line. If they were straight, if those, okay, since you mentioned it, let's just write this down. What do you call a chord that contains the center of the circle? A diameter, huh? Okay, and you guys have heard that word before, diameter. So if CB was a diameter and AD were a diameter, then we would have vertical angles, right? But I don't know that those are diameters. I don't know that, like if I drew CE and I just kept going straight, I don't know that I would hit B. Actually, my picture doesn't even look like it would. So we can't use vertical angles here. But what can we say about the triangles AEB and CED? How are they congruent? Okay, so you have in a circle you have a radius, and you gotta take advantage of that radius. And you'll see in almost every problem I have, you gotta take advantage of that radius. So All these are congruent to each other. And then I'm telling you that AB is congruent to CD, right? And so the triangles are congruent, which means that this angle here is congruent to this angle here. So CED and AEB. Not because they're vertical angles, but why? CP, CTC, corresponding parts of congruent triangles are congruent. Now, if those angles are congruent, then what else is congruent? Measure of arc AB and the measure of arc CD, because the measure of arc AB is that angle, right? So like if this is 40 degrees right in here, then this is 40 degrees. And if this is, those are congruent, they're both 40, and then this would also be 40. So that's the idea there. And I'll take away the triangle so you can see the key pieces here. If you have two chords that are congruent, then the arcs that they intercept are also going to be congruent, and the measures of those arcs will be congruent. Okay. It also works the other way around. You could start with if the measure of the arcs are congruent or equal, then you can get to the fact that the chords themselves are congruent. Okay. Maybe I'll do that quickly for you too. So let's say we don't know that the chords are congruent yet, but we know that the measures of the arc, say they're both 40 degrees. So here's the center of the circle. So because those are 40, these would be 40, right? That's the measure of your arc is equal to the measure of the central angle. And then these are all radii are all congruent to each other. And so the two triangles would be congruent by what now? Side angle side. And because the triangles are congruent, corresponding parts are congruent, and we get AB is congruent to CD. So just to know that that relationship, if the chords are congruent, their arc measures are congruent, and vice versa. Okay, so let me give you another example that uses this fact. So we have another circle, center A. I'm going to put 4 points on the circle here and connect them this way. I'm going to label the points B, C, D, and E. I'll give you some information here. So first of all, this is circle A, telling you that the center is A. The measure of BAE, sorry, it should be angle. Angle BAE is 100 degrees. The measure of CD, the arc, is 120 degrees. The measure of arc ED is 2x squared plus 5x plus 73 degrees. And I want you to solve for x. So again, you just start marking out the circle. What's given, they tell you, okay, center's A, BAE, that's right in here, is 100 degrees, which means that the arc measure here is 100 degrees. They tell you CD is 120, so I'm going to put 120 over here. So that's from CD. Oh, and I'm missing a piece I meant to give you. Otherwise, you get stuck here, huh? I meant to tell you that BC and ED are equal length. Okay, so the length from B to C is the same as the length from E to D, although it doesn't look that way in my picture. But I'm telling you that's true. So if I tell you that, what else has got to be true? What else is equal? The arc. So BC, let's call that y degrees right now, and this is also going to be the same, right? Because these are both congruent to each other. And so if we add up all four of those angles, we get 360. So we could solve for y, and let's do that. So y plus 100 plus 120 is 360. So 2y plus 220 is 360. 2y is 140. Y is 70. So we get 70 degrees for each of those. And then our equation here, it says the measure of ED is this equation 2x squared plus 5x plus 73. So we can take that and set that equal to 70. And now we have something to work with to solve for x. So before you grab those quadratic equations, do as much as you can with the circle to kind of figure out what it's equal to, and then work with it. So it's quadratic, so we set it equal to 0 and try to factor it. And you just need to know, okay, which type of factoring are we going to use here? This is the kind where you have a trinomial, you got 3 terms, and you take the first and the last number, multiply them together, and take the middle number, right, and put it down there. And you're looking for 2 numbers that multiply to 6 and add to 5. 3 and 2. And once you find those two numbers, excuse me, you're going to split up the middle term, the 5x, to 3x and 2x. So you're going to get 4 terms. So 2x squared plus 3x plus 2x plus 3 is equal to 0. And then once you get the 4 terms, you factor by grouping. So you create 2 groups, and you factor out the GCF of each group. So the first group, you factor out an x. Second group, you factor out a 1. You got one more move here. Now you picture it as 2 terms separated by that plus sign, and they both have the common factor of 2x plus 3, so you factor that out, and you're left with the x plus 1. So that's the factoring process there. Once you've factored, set your factors equal to 0 and solve, and you get 2 answers. -3/2 and -1. Any questions on that one? I needed to give you that extra piece of information that the chords were congruent. Sorry about that. But this is, again, kind of the type of problem that you're going to see. All right, there's one more thing I want you to know about circles and chords, and then we'll look at a few more examples with that, and then we'll be done with our notes. So that is the case where if we have a circle with a chord, and if we were to draw a segment from the center of that circle to the chord and make it, well, I'll hold off on what we're going to make it. So if we have that picture, okay, if I tell you that CE is perpendicular to AB, then what do you think true as well? If those are perpendicular to each other, what else can be true? That AE is going to be congruent to EB. So again, just kind of talking through why this might be true, and I'll draw my triangles to help us. Why might that be true? So if they're perpendicular, so if we form a right angle here, what's a quick way to say, well then AE's got to be the same length as EB? Okay, so you can use you can show that the triangles are congruent by hypotenuse leg, and then corresponding parts are congruent. Or you can use the perpendicular bisector theorem. Both of those would work. Okay. Also know that it works the other way around. So if we had AE congruent to EB, then we can say they're perpendicular by the converse of the perpendicular bisector theorem, or you can use triangle congruence as well. Okay. So just again, we're not emphasizing the proving, but a couple of these results we want to be able to work with. And let me show you an example that uses this result. I need your thinking caps on here for the next few problems. All right, so we got this circle here, and here's our center, and I'm going to give us 4 points. So this is C, D, A, and B, and so we're working with circle C. So C is the center. I'm going to tell you that CD is perpendicular to AB, that CD is 5, and AB is 12. And I'd like you to find the radius. Let me know when you have it. You have it? What do you got, Nathan? Root 61, good job. Root 61. Nathan, can you tell us how you did that? Hold on. So, okay, tell us CD's 5, yes. Okay, because it's perpendicular, it bisects this chord. Okay. Okay, so the distance from C to A is our radius. And we get that right triangle using Pythagorean theorem. We could say that r squared, or radius squared, is 5 squared plus 6 squared, and then you got it. Very good. So 25 plus 36. So the radius is the square root of 61. Okay, so always be mindful of the radius. Okay, and you can put it anywhere you want to help you out with the example. Keep that in mind for this next one. It's going to be a little trickier now. Okay, so on this one, we're going to label A, D, E, B, and C. And circle A, so I'm telling you the center's A. BE is equal to CE. AD is 12. And ED is 7. I'd like you to find BC. Again, be mindful of the radius. Can we make a right triangle? All right, that's the key. Like, if I do this, and first of all, is it a right triangle? Can I put a 90-degree angle here? Yes, because it tells us that BE and CE are congruent, and this is from the center of the circle to that. So so we can't put that 90-degree angle there. What can you tell me about the side length of this triangle? Do we know AC? Yes. What is it? It's 12 because I give you AD. That's a radius. Be mindful of the radius, and that's a radius right there. So that's 12. And then they tell us this is 7 from D to E. So what is it from E to A? 5, because it's got to add up to 12. And so now I have 2 of the 3 sides. So I'm going to call this side X. And we know this is also X. And I could solve for X and double it for my answer. Is X going to be 13? 5, 12, 13? No. Good. Because X is a shorter side length. So you got X squared plus 5 squared is 12 squared. You get 119, is that right? So X is root 119. So what's BC? 2 root 119. Okay. All right, last example. See if I can squeeze it in here with you guys. I want you to see it. Not as much thinking, but a lot of working on this next one. Let me tell you got this right triangle here. This is X minus 1, this length. The hypotenuse is X plus 1. The length, the third side of the triangle is X minus 3. And let's just solve for X. What do you think we're going to have to use to solve for X? Pythagorean theorem. So you take the 2 shorter sides, the X minus 1 squared plus the X minus 3 squared, and set that equal to the hypotenuse, X plus 1 squared. And so you're going to have to find out what X minus 1 times X minus 1 is, and add that to X minus 3 times X minus 3, and set that equal to X plus 1 times X plus 1. Multiply all that out. and then simplify, and then set one side equal to 0, and then factor and solve for x. Go for it. What are we getting? You guys get this far? X squared minus 10x plus 9 equals 0. You multiply it out, simplify it, subtract it. That's the kind of the multiplying, simplifying part. And then you factor it. And you end up with x is 9 and x is 1. But then you throw out the 1 because that would give you a negative side length, and you get x is 9 as your answer. Okay. We'll talk more about this tomorrow. Homework is 1 through 20 from the first homework, okay?